Okay, so what I have in day 2 of using trapezoid and Simpson's rules is just some more examples. So we're going to start to see today an example. The other example I did yesterday was one we could actually compute the definite integral for. This one we definitely can't compute it. We don't know how to do that. We couldn't make a U statement, so we'd have no other choice to do but trapezoidal rule and make an approximation or use Simpson's rule. So I'm going to do both of those in this problem. Now, if you notice, I started to break this line up, and I wanted to go ahead and start to do that because we're talking about breaking things up into 4 subintervals. So one of the things I want you guys to think of is some of you might have trouble breaking up pi over 2 and pi into 4 subintervals, but really think about this as being 1/2 and this being 1. And so if you were going to find values in between there, you'd say, well, what value is between 1/2 and 1? And you'd say 3/4. So that's why I've written 3 pi over 4. And then what values between 1/2 and 3/4? Some of you would have problems doing that. So what I would tell you to do is make a common denominator like 8, and this would be 4/8, and then this would be 6/8. And so what number is between 4/8 and 6/8? Well, you'd say 5/8. So I'll be using 5 pi over 8. And then the last value, of course, then has to be 7 pi over 8 because this has to be between 8/8, 6/8, and 8/8, which is 7/8. So that gives me my 7 pi over 8. Those would be the values that I'm using when I'm plugging into the function. So remember, trapezoidal rule says b minus a, so I'm going to take my b value pi minus my a value pi over 2 all over 2 times however many subintervals I have, which in this case is 4. We'll go ahead and simplify this first before getting started writing the rest of this. This computes into pi over 2 divided by 8. So really that just means I have pi over 16. So I'm going to start with pi over 16, and now I'm going to multiply all that through. Remember, the coefficients on the trapezoidal rule are 1, 2, 2, 2, 1. So I'll be writing down what the value of the function is at pi over 2 first of all. So I'm going to write down, I have the square root of pi over 2, sine of pi over 2, plus I have a 2 out in front. 2, let's see, the next value is 5 pi over 8, and then sine of 5 pi over 8. My next coefficient is a 2, and I have the square root of 3 pi over 4 times the sine of 3 pi over 4, plus my other coefficient is 2, plug in 7 pi, so I'd have square root of 7 pi over 8, sine of 7 pi over 8. I'm trying to squeeze this in here. The last one has a coefficient of 1, which I'd have the square root of pi and then sine of pi. And I ran out of room there. But when I would multiply those all together, and you guys are going to have to take time to compute that on your calculator. These are each separate terms. Figure out what each of those are. Add them all together and then multiply by pi over 16 at the end. You should find your answer to be approximately 1.430. Now what I'm going to do is I'm going to write down the Simpson's rule for this exact same problem. So I'll be using the exact same numbers, pi over 2, 5 pi over 8, 3 pi over 4, 7 pi over 8, and pi, for the exact same reason as I did on the last one. I needed 4 subintervals. Simpson's rule said upper bound minus lower bound all over 3 times the number of subintervals, which is 4 in this case. When you simplify this, you end up getting pi over 24. And then I'm going to plug in those values. Remember, Simpson's rule has 1, 4, 2, 4, 1 for its coefficients. So I've got the square root of pi over 2, sine of pi over 2, plus 4 times square root of 5 pi over 8, sine of 5 pi over 8, plus 2, the square root of 3 pi over 4 times sine of 3 pi over 4, plus 4, the square root of 7 pi over 8, sine of 7 pi over 8, and then plus the square root of pi, sine of pi. When you were to compute all those, you would end up with approximately 1.458, very close to the other answer.